My name is Seth Lloyd. I'm professor of quantum mechanical engineering at MIT, and I'm here to tell you about quantum machine learning. Machine learning is how computers learn patterns in data, and quantum machine learning is about how quantum computers and other quantum information processors can learn patterns in data that cannot be learned by classical machine learning algorithms. Now, why might we hope that quantum mechanics might help in learning patterns in nature? There's a simple reason. Quantum systems are famous for generating strange and counterintuitive patterns that cannot be generated by any classical system, including a classical computer. Quantum mechanics is weird. Now, we can reasonably hope that in addition to be able to generate such strange and counterintuitive patterns, that quantum computers could also recognize strange and counterintuitive patterns that cannot be recognized by any classical computer. So quantum weirdness might allow us to help in understanding the weird features of nature itself. Now, there's a second reason why quantum mechanics might be helpful in finding patterns in nature, and that is that a large amount of the classical algorithms for finding patterns in nature, classical machine learning, is based on linear algebra, on the manipulation of high-dimensional vectors of data. And quantum mechanics is entirely about linear algebra. So for example, if we have a classical vector of data, which I'll call x, and it belongs, let's say, in a high-dimensional complex vector space, then we could map this into a quantum mechanical vector of data that has the same components. It looks exactly the same, but the difference, and this is the key difference in terms of getting large speedups for quantum computers, is that this classical vector takes order n bits to describe, whereas this quantum vector takes log n bits to write down. Because if I have little n is equal to log n quantum bits, then n qubits lie in a very high-dimensional space. The whole formalism of quantum mechanics is based on vectors in very high-dimensional spaces. And then the natural dynamics of quantum systems will take these vectors and multiply them by matrices. And as long as we can do these matrix manipulations in an efficient fashion, we'll find that many quantum algorithms for machine learning will take, instead of taking time a polynomial in n, like n or n squared, will take time a polynomial in log n, such as order log n squared. And to emphasize this, let me just tell you about how a few of the standard classical linear algebra subroutines, the BLAS, basic linear algebra subroutines. Let me just show you how those translate into the quantum basic linear algebra subroutines, the Q-BLAS, as I call them. So let's, for instance, take a very famous classical subroutine, the fast Fourier transform. The fast Fourier transform, which is a vectorial operation in which I basically do the Fourier transform of this vector x, it takes time order n log n on a classical computer. This is remarkably fast because it actually you have to multiply by an n by n matrix, but it turns out this matrix is sparse, and so you can actually perform this in order n log n. The corresponding quantum operation, which is exactly the same when written in the components of this vector, the quantum Fourier transform, this takes time order log n squared on a quantum computer. So there's an exponential speedup. So for example, if n is equal to 10 to the 12th, a terabit of data, then n is log n is just equal to 40 bits. So I could have a terabit of data, and then I can map this terabit of data onto a quantum state that has only 40 quantum bits, 40 qubits. So you see that the compression is tremendous. Similarly, to do the fast Fourier transform over this data takes time, order something like 10 to the 14th steps, whereas the quantum Fourier transform would take time on the order of 1600 steps. A tremendous compression in the amount of time and effort it takes in order to manipulate this data. Other famous algorithms, classical algorithms, include finding eigenvectors and eigenvalues of sparse or low-rank matrices. This typically takes time order n squared. And the quantum version of this, which is called the quantum phase algorithm, again takes time order log n. So you can actually do you can find, diagonalize a sparse or low-rank matrix and find its eigenvectors and eigenvalues in time order log n on a quantum computer. Actually, I think it's order log n squared on a quantum computer. And you can do this much, 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 much faster than you can on a classical computer. Note here that if I try to find the eigenvectors and eigenvalues of an n by n matrix where n is 10 to the 12th, then I have to do 10 to the 24 operations, more than Avogadro's number of operations in order to do this. This is completely out of the reach of any classical computer now and for the near future. Whereas a quantum computer, again, could do this operation in around 1600 quantum logic operations, which we expect to be in the range of quantum computers within the next 5 years or so. Finally, we can do things like matrix inversion. So we're given a matrix A, and we're given a vector B, and we want to find the x such that AX is equal to B. That is, x is equal to A inverse times B. Again, classically, this can take time order n log n to order n squared, depending on what kind of matrix one's inverting. But if we do the quantum mechanical version of this algorithm, so we have a matrix A, and then we are trying to find a quantum state x such that this matrix times this quantum state is equal to B, then we can use the natural fact that in quantum mechanics, the dynamics of quantum mechanical systems involves multiplication by these matrices to construct the inverse of this matrix and to implement it and find this vector x. And again, we can do this in time order log n squared. So if we can construct some kind of operations, if we can do some kind of data analysis that's based on these sorts of linear algebraic techniques, and crucially, if we can perform this initial mapping from classical data into a quantum state, then we can actually have the hope for doing transformations for analyzing data sets that are much, much larger than we ever expect to be able to analyze using classical methods. Let me just say briefly a word about this. You see that the key point here is not, well, part of the key point is these quantum algorithms, which have been developed over the years by a bunch of clever people to show how you can exponentially speed up the corresponding classical algorithms. But the key point here for this kind of quantum machine learning algorithm is to show how you can take a large classical vector of data and to map it into a quantum state. And for this, you need a device that is going to take classical data defined, for instance, in the mirrors on a CD, on a compact disc, or classical data defined in pulses of light that are going down a fiber optic cable, or classical data that's stored in capacitors in an integrated circuit, and you have to be able to map it into a quantum state. The device that will do this for you is called a quantum random access memory, or QRAM. And one of the main technological issues and problems facing quantum machine learning for these kinds of tremendous speedups is how do you build a quantum random access memory? I'm currently working with a bunch of collaborators to show how you can build these out of superconducting circuits or out of ions in ion traps by tickling them with light to map the classical state of the light into the quantum state of the ions. And one can also imagine mapping them into quantum light, into the squeezed and entangled states of photons on an optical table or in an optical chip. I want to emphasize that this is the most difficult technical part of this matter, but also that building a quantum random access memory is likely to be a heck of a lot easier than building a full-blown large-scale quantum computer that can do things like factor large numbers and break public key cryptosystems. So I think it quite likely, again, that in the next 5 years or so, we should have maybe not quantum random access memories that can map 10 to the 12th bits onto 40 qubits, but certainly ones that can map 1,000,000 bits onto 20 qubits or 1,000,000,000 bits onto 30 qubits. Okay, so quantum computers can perform linear algebra much more efficiently than classical computers because quantum mechanics is all about linear algebra. Now let's look at the kind of problems that we could actually solve with this tremendous speed up that's afforded by quantum computers. So there are many classical machine learning protocols that are done solely in terms of linear algebra. So let me actually give an example of some of them right here. So one of them is cluster finding. So we're given several clusters of data. And let's say that there's labeled data. So we know which data, which cluster each of our existing data points falls into. So here we have 3 clusters. We've got the pink cluster, the green cluster, and the yellow cluster. And now we're given a new point, and we want to find which cluster it should be associated with. I've drawn it close to the green cluster, so it could be associated with that. Well, a very straightforward application of quantum computation allows us to calculate the mean values of these clusters. I'm drawing that like these blobs in the middle. Let's make sure I get the right color. Here's the mean value for each cluster. And then it's a straightforward matter to decide whether this dot is closer to this blob, closer to this blob, or finally closer to this blob. And this is something where if these data points are very, very high dimensional, it can be quite difficult to figure out, do the classical version of this, because calculating these distances can be hard. One might also have to do things like include this with asking whether this point is closer to the Fourier transform of the points here or there. Or you would have to, if you have to do a Fourier transform, then you can do it exponentially faster on a quantum computer. So this is a very simple kind of algorithm that gets sped up by quantum computation. And a similar algorithm, also a very fun kind of algorithm, that is called a support vector machine. Again, this is a case where you have blobs of data. You have labeled clusters of data. I'm going to draw 2 of them here. Getting very good at drawing little blobby-like clusters of data. And the goal of your algorithm is to construct the optimal separating hyperplane between them. This optimal separating hyperplane is a hyperplane that has the largest margins between the clusters of data. This is a problem that involves solving this kind of problem that B is equal to A inverse times X. It's a problem that involves matrix inversion. And so solving this on a classical computer, again, this could take a very long time if we have many, many data points and that these data points are very high dimensional. But again, on a quantum computer, it can be solved extremely efficiently. And so you can identify, this optimal separating hyperplane, and if somebody gives you a new point, you say, aha, it lies on the pink side of the hyperplane, so I'll identify it with this cluster here. Again, this is a problem that receives an exponential speed up from quantum computers. Another nice linear algebraic based algorithm is the following. These are all, I'm going to draw lots and lots of these these data points here. So here is another blob of data. It sits in some funny shape like this. And the goal of your algorithm is to find the proper axes along which to group this data. So this is what's called principal component analysis, or PCA. This is something that, again, takes time order n squared on a classical computer, but if you do the quantum version of quantum principal component analysis, you find that you can actually do it again exponentially faster. These kinds of algorithms are used all over the place for things like handwriting recognition. For instance, this blob could be scrawled versions of ones, this blob could be scrawled versions of threes, this blob could be scrawled versions of sevens, and you want to find out which digit should be assigned to which blob. Principal component analysis lies behind the Netflix algorithm. So if you're given a bunch of users, and each user expresses their preferences for a set of movies, and now you have a new user, and you want to find out which movies that user might like, then if you have a multi-dimensional blob in space of all the movies and all the preferences, these principal components turn out to be the same as the different genres, rom-coms or horror films. And you can find, if you have a new user, you find that this new user, that it seems to be oriented more along the rom-com axis, so you can recommend to him Sleepless in Seattle. This, by the way, this principal component analysis is basically the way that Netflix actually does analyze their data. They have a huge database. It takes them the whole day on a gigantic set of classical computers to perform this analysis. On a quantum computer, you could do this again in a very brief time and provide quantum recommendations to your quantum users. Here is another fun kind of algorithm, if I may say so. So I'm going to draw another blob. I think I'll draw it in blue this time. Here's another set of data points. And I think you'll agree that this data has a hole in it. There's a hole in the data. But how do I tell that there's a hole in the data? If I look up close, the data's all holes. But if I look from further away, I see this kind of blobby thing. It's kind of the points mushed together. I say, oh, look, it's a blobby thing with a hole in it. And it turns out that this is a method for finding these topological features of data, where you can map this again into the problem of finding the eigenvectors and eigenvalues of some huge honking high-dimensional matrix. And by doing that, you can count the number of holes and voids and connected components in your data, and then you can track them as you move through the data by looking closer and looking further away. So these are fun methods for quantum learning that are quantum machine learning that are based solely on linear algebra. But then we can also look at other classical machine learning methods, such as deep learning. Deep learning, when I first heard about it, I said, wow, this is amazing. Classical computers are going to teach us about deep things about the world, like truth and love and happiness and how to get a date on Saturday night. But no, I'm afraid it's not like that. What deep learning means is that you have a deep network where things are interacting with each other. I'm just drawing this network. These lines are just bits, if you like. Here are things interacting with each other. They should look blobby because it should look a bit like a set of neurons and things. And then you have weights that tell you the responses of these different artificial neurons that are processing these signals. And the idea is that if you adjust these rates properly, then if somebody puts in a scrawled 7 into the input of this circuit, which I've drawn at the bottom, at the top, one of these neurons fires that says, oh, it's a 7. This is the basis for a huge amount of deep learning protocols, including voice recognition software, handwriting recognition software. People basically, if they have any problem, they don't understand it these days, they say, let's whip out the deep neural network and give it a ride. So the interesting thing about deep learning, one of the reasons why it's so effective is that you can show that such deep neural circuits actually can encode any kind of classical logic operation in them. They're effectively computationally universal. This has been known since McCulloch and Pitts, who first introduced these deep artificial neural networks back in the 1940s. But if we actually make this quantum mechanical, so we have deep quantum learning. So all of our circuits now represent quantum logic gates. The parameters, these weights, which we can adjust to represent the parameters of these gates. Then now, and the things that we put in are quantum states. The outputs themselves are also quantum states. This is how you make something quantum mechanical. You put this funny thing called a Dirac bracket around it. So a good way to make something like Google quantum mechanical is to put these brackets around it. This, by the way, is the logo for the Google Quantum Artificial Intelligence Group. If you make this into a quantum mechanical deep learning circuit, then this deep learning circuit inherits all the virtues of quantum computing. So we know that it's capable of computing things that cannot be computed classically. For example, these kinds of problems up here. So we know that there are problems that you could learn in a deep quantum learning circuit that you couldn't possibly learn in a deep classical learning circuit. So let me just conclude by saying quantum mechanics is weird. Quantum systems can generate weird patterns that are very hard to generate classically. But quantum systems can also learn and recognize weird patterns that can't be recognized classically. And the reason that they can do this is that quantum computing and quantum mechanics is all about linear algebra. But with a very small number of quantum bits, you can have states that represent vectors in a very high dimensional vector space. And then quantum computers can be used to do linear algebraic operations such as fast Fourier transforms, finding eigenvectors and eigenvalues, and inverting matrices exponentially faster than you can do classically. And I'm very much looking forward to the time in the very near future, I suspect within the next 2 to 5 years, when we'll be able to build sufficiently big quantum computers to build quantum random access memories to load and embed classical data into quantum systems so that we can realize the power of quantum machine learning.